Okay, here is the second practice exam. I'm going to come over here to homework and then scroll down the homework list, and all the way at the bottom the practice exams are down here. We've completed practice exam 1 for chapters 1 through 3. Practice exam 2 is over chapters 4 and 5. And I've already created a third one too, but we'll just look at the second one today. 25 questions, similar to the 25 on the exam. So question 1 gives me a list of probabilities and wants me to check off any of them that are impossible probabilities. And the ones that can be probability are numbers between 0 and 1, including 0 and 1. So if you're not between 0 and 1, then you cannot be a probability. Any negative number cannot be probability. 3/5 is okay because 3/5 as a decimal is 0.6, that's between 0 and 1. 0 and 1 themselves are okay. 0.05 is between 0 and 1. Now the square root of 2, if you didn't know this, in a calculator you could hit square root of 2. And it says it's 1.41, but that's bigger than 1, so that's impossible. Square root of 2 cannot be a probability because it's bigger than 1. And clearly 1.32 is bigger than 1. 5/3 as a decimal is bigger than 1. 5 divided by 3 is 1.6 repeating. So that's also too big. Probability can't be bigger than 1 or less than 0. So anything bigger than 1 or negative is taken out. 20 of the 100 digital DVRs in an inventory are known to be defective. What is the probability you randomly select an item that's not defective? So doing the probability of not something is an idea called the complement. And the complement's kind of the opposite scenario. Since 20 out of 100 are known to be defective, 20 out of 100 are known to be defective, 0.2 is the probability of a defect. So the probability that you don't have a defect is simply 1 minus that. You always do 1 minus whatever you have to get what you don't have. That's the complement idea, is doing 1 minus it. It gives you the opposite. If there's a 20% chance of rain today, then there's an 80% chance it won't rain. That's the opposite scenario. So defective is 20%, not defective is the opposite, 0.8. And the opposite comes from 1 minus it. You toss a coin and randomly select a number between 0 and 9. What's the probability of getting tails and selecting a 5? When you encounter and probability questions, there's 2 cases to worry about. One case is easier if you know that the 2 events are independent of each other. And flipping coins and selecting numbers don't affect each other, so they are independent. If 2 events are independent, doing their and probability is easier. You find the probability of getting tails, 1/2. You find the probability of selecting a 5 out of 10 numbers. There's 10 numbers between 0 and 9. That's 1/10. And then in an and, we can multiply those answers together. 1/2 times, let me do it this way, 1/2 for the flipping the coin and getting a tails, times 1/10 for drawing a 5 out of 10 numbers, getting a single number 5. So this is 1/20th, or as a decimal, 0.05. 1/20th is 0.05. And that's the choice, the first choice, no, I'm sorry, the second choice, 0.05. If a couple were planning to have 3 children, the sample space summarizing this would be these 1, 2, 3, 4, 5, 6, 7, 8. They want you to do a similar one if you just have 2 children. So you got boys and girls with 2 children. I always like to do this, and the first child's either boy or girl, the second child's either boy or girl from each one of these. This is a good way to list your whole sample space. If you follow each path to the end, boy, 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 girl, girl, boy, girl, girl. There's your sample space for having two children. If you have two children, one of these four genders is going to happen. Either you're going to get two boys, boy, boy, comma, or you could get boy first and girl second, comma, girl first, boy second, comma, girl, girl is the fourth option. And the reason it's good to know your sample space, once they give you questions about probability, all probability is over a total. So the total is how many things are in your sample space. We have 4 items here. So any probability question they give us, we're going to start off as something over 4. What's the probability of getting 2 girls? Only one of these 4 has 2 girls in it. So 1 out of 4 is the probability of 2 girls. By seeing the sample space, we can just count it and see that it's 1 out of 4. The probability of getting 1 boy and 1 girl, and here it doesn't specify that order matters. So there's 2 scenarios where that happens, 1 boy and 1 girl, or 1 girl and 1 boy. There's 2 different ways to get 1 girl and 1 boy. So that's 2 out of 4. Always reduce fractions when you can. So 2 out of 4 reduces to 1 out of 2. So sample space can help so you can see all the possibilities. Determine whether 2 events are disjoint. I always answer this in the following way. Randomly select an SUV vehicle that's in an assembly line and getting one that's free of defects, or randomly selecting one that has a dead battery. To be disjoint means they need to be totally separate and you can't do both at the same time. Now it's a little tricky because the definition has a negative in it. The definition of disjoint is when you can't do both at the same time. So I always ask myself, can I have both at the same time? Could I get a car that's free of defects and at the exact same time it has a dead battery? And the answer to that is no, you can't have both of those at the same time because if the battery is dead, that's a defect. So you can't do both of these at the same time, so then yes, it is disjoint. If you answer no to the question of can you do them both at the same time, then the answer is yes, it is disjoint, and vice versa. Another example would be select a person at a high school. Could they be a freshman or a senior? So can you be a freshman and a senior at the same time? No, you're either a freshman or a senior. You can't be both at the same time? No, so then yes, that would be disjoint. These cannot both happen at the same time. So this is disjoint. They're disjoint because they cannot occur at the same time. Okay, we want the probability a pedestrian was intoxicated or a driver was intoxicated. So or questions are a little bit trickier than ands. Here I've got intoxicated driver going this way, and then you got intoxicated pedestrian going downward. So you get 4 values in the table. And the probability the driver was intoxicated is this path right here. The probability the pedestrian's intoxicated is this path right here. There's basically 3 values that are good in my scenario of what are good cases. It's a little different than trying to add up the drivers, add up the pedestrians, and just adding those 2 numbers together, because you're double counting these. This is a case that's not disjoint. You could be an intoxicated driver and intoxicated. You can't be both intoxicated driver. Oh, you could be. Because these overlap each other, you can be both intoxicated as a driver and a pedestrian. So you could have been driving for a while, got out and started walking or something. But if the 2 things overlap each other, they're not disjoint. Disjoint is when they're separate. So because of that scenario, I have to add up I have to add up the three good cases. The three good cases are 52, 76, and 208. Those are the three scenarios where you're either an intoxicated driver or you're an intoxicated pedestrian. So that's my, and then probability, you always want to know how many good cases are there divided by how many total cases there are. The number of total cases is all of those plus the 517 that I haven't used yet. So the total number is 853. There's 336 good cases divided by 853 total cases. So the probability is 0.3939 on and on. Now here's where on a test you've got to be real careful. Before you put an answer into any problem, always read what they want you to put in there. Round to 3 decimal places. If you don't do that, they count it wrong even if you, in essence, had the right answer. Round to 3 decimal places. 1, 2, 3. Go to the third place. If the next digit's 5 or higher, you add 1. Add 1 to 3, that would make it a 4. 394. 0.394. Okay, probability somebody is 60 and over. Who responded? So this is more, this isn't an or case. 60 and over is this column. Responded is this row. Those two meet each other right here at 203. So the number of good cases is 203. The number of total cases is all of these numbers added up. So I just have to add all the numbers. 74 plus 15 plus 256, 24, 246, 37, 137, 30, 139, 39, 203, and 61. My grand total is 1161. The number of good cases was 203. That's where the respondent met the 60 and olders. Divide by the grand total and round to 3 decimal places. 0.1748. So since the fourth place is an 8, I have to add 1 to the 4, 175. 0.175. Okay, hang on. What happened here? Someone who is 60 and over who responded. It's 203. I also missed added somewhere. Double check the adding. 74, 15, 256, 24, 246, 37. Oh, right there I didn't put a 137. I put 37 twice, so let me hit second enter, and I can change one of these 37s. One of them should have been 137. So that made my grand total wrong. Move right here where you want to add a 1, and I'm going to hit second and the delete button, and then I can type a 1 and it'll slide everything else over. So the actual grand total should have been 1261. 203 divided by 1261 is 0.1609, so the 9 is going to make it 161. 161. So here's a good, perfect example where if I was taking a test, I would have missed that question because I had a typo while I was adding up numbers in my calculator. Be real careful. There's no time limit on the test other than the testing center hours. You might want to double check anything. If you have a long calculation on a calculator, double check you typed it in correctly. Okay, consider a bag that contains 229 coins, of which 6 are rare Indian pennies. Part A, when one of the pennies is randomly selected, it turns out to be one of these special Indian pennies. When another one of the coins is randomly selected with replacement, it's also one of them. So determine whether they're independent or dependent, because if they're independent, that'll make things a lot easier. Independent is when one trial doesn't affect the next. So your probability of drawing one of these special pennies There's 6 of them out of 229. The probability is 6 out of 229. You get one of them. Now, when you go draw the second one, it depends whether you put that one back or not. If you did not put it back, there would be one less of those in the bag and one less total coins in the bag. Then drawing the second one, it would be affected by what happened first. But the key thing here in this problem is it says with replacement. If you put it back in, then the second draw is identical to the first draw. You still have a 6 out of 229 chance of drawing it the second time also. So therefore, these are independent events because the occurrence of one does not affect the other. I get the same probability both times. If it was dependent and you left the coin out, the second one would have been 5 out of 228, and the probability would have been different. So then it would have been dependent, it would have mattered. But it's nicer when it's independent because then we can just multiply the answers together. The probability of getting 2 coins in a row by putting them back in each time is each one's probability times itself. And it says round to 6 decimal places, so you've got to be real careful. A lot of them ask for 3, but this one asks for 6. And the reason is you sometimes get this weird answer like this. 6.86485765 e negative 4. You're going to see this more throughout the course where you get this e negative 4 at the end. That's the calculator's way of doing scientific notation. Times 10 to the negative 4. They can't type that for some reason. So you have to go back here where the decimal is and move 4 places to the left. 1, 2, 3, 4. Times 10 to the negative 4th is the same as 0.0006864, on and on and on. So rounding to 6 places, 1, 2, 3, 4, 5, 6. Here's where I want to round to. The next digit's not 5 or higher, so the answer would be this. 0.00686. 0.00686. Okay, when 12 job applicants are examined for a certain job, none of them test positive. We want to write the complement of that. There's a rule that the complement of none, if you're trying to do the probability of none of something, the probability of none is the probability, the complement of it, I should say, it's not equal to it. The complement of none is at least 1. Because if you made a list, say you have a car with 4 tires. You have 4 tires on your car. How many tires on your car are flat when you go out in the morning? You could have 0, 1, 2, 3, or 4 flat tires on a given morning. So the probability of none is this case right here. The probability of no flat tires is a single answer. What's the opposite of that? The opposite is everything else. The opposite is 1 or more. Another way to say 1 or more is to say at least 1. But there's a nice little rule. If you ever see what's the complement of none, the complement of none is at least 1. If you remember that little rule, you can get this question right, because there's one choice that says at least 1. At least 1 positive is the complement of none. Okay, the accompanying table displays results from experiments. Okay, pull that up. Find the probability the subject told the truth given that they have a negative test result. This is another concept in statistics called conditional probability. And it's written like this: probability of A given B with a vertical line. This is read given. So we want the probability that the person told the truth given that they tested negative. So what you do for these is, the formula is you do A and B divided by B. The probability of A given B is A and B divided by B. So we need the probability of the truth and testing negative divided by negative. Well, in a table, you can always find an and where they meet each other. Put your finger on truth, put your finger on negative. Here's negative, and lying is not telling the truth, so not lying is telling the truth. Where does negative and telling the truth meet? They meet each other at 31. So the top of this is 31, and then we divide by the negative cases. There's 2 negative cases, 11 and 31. That's a total of 42. So it's where they meet each other divided by all the second one, all the negatives. 31 divided by 42. Which is 0.738 if they want 3 decimal places. Round to 3 decimal places, 0.738. Now, they give you the opposite case to show you a point here. If we do the probability of truth given negative, we get that answer. Or what if we reverse it to negative given truth? Well, the numerator is still the same. You got both of these together, negative and truth. But now we divide by the truth column. You always divide by the second one. So negative and truth still meet each other at 31. But now the truth is what we divide by, which is this column, 46. So now we're dividing by 46 instead of dividing by 42. So one time you're using this row, now you're using this column. So it depends what the given part is and what the denominator is going to be. So now it's 31 divided by 46 instead of 42. 6739, so that'll be 674. The 3 decimal places. Are these 2 values equal? On a rare occasion they might equal each other, but usually they're not. And you can see here they're not. And that's the point. It does depend which one you're given. Are you given negative test results, or are you given the subject told the truth? That makes a difference in the answer. It's not usually the same. Okay, in horse racing, a trifecta is a bet that the first 3 finishers in a race are selected, and then you select them in the correct order. Does a trifecta involve a combination or a permutation? Combination is when order does not matter. Permutation is when order does matter. And in a horse race, order matters because you'd rather be first than second or third. So it's definitely a permutation because order matters. The order of the first 3 finishers does make a difference in a horse race, so this is C, that it's a permutation because the order matters. Now, if you're going to make a CD with 10 of your 29 favorite songs, the order songs go on a CD doesn't really matter because they're either on there or they're not. So you just want to be one of the 10 songs on the CD, and this is an example of a combination because the order doesn't matter. Plus, they tell you in the problem how many different combinations of 10 songs are possible. So there's a quick way to do this in your calculator. You're trying to pick 10 out of 29 songs, and order does not matter. So we put this bigger number first, 29, hit the math button, right arrow over to probability, and you got NPR for permutation, NCR for combination. So I would select combination, because not only does order not matter here, the problem even says it's a combination. Select that one by pressing enter, and then you put the smaller number last. 29 combination 10, and this is going to be a gigantic number. 1, 2, 3, 1, 2, 3. It's 20,030,010. There's over 20 million different ways you could make this CD. Is it practical to do each combination? Certainly not. Nobody would want to make 20 million different CDs. So it's not practical because the number of combinations is very large. Too many to do. A presidential candidate plans to begin her campaign by visiting capitals in 4 out of the 45 states. So they're not using every state, but what is the probability she selects the route of 4 specific capitals? So here we have to decide, is this a permutation or a combination? Would order matter or not? If you're flying from state to state, I would think order matters, because if you're in Virginia, you wouldn't want to go all the way out to California, then all the way back to Kentucky, then all the way out to Arizona. It would be a better strategy to go in order, and so you don't have to make all that extra flying around. So here, order seems to matter. It's a permutation. So I'm trying to pick 4 out of 45 first. Same deal. Pick the bigger number first. Math, probability, but this time choose permutation number 2. And then put the 4 last. The bigger number is always first. There's 1, 2, 3. There's 3.5 million different ways you can do this. Now, there's a difference in the questions too. The previous question said, how many ways can you do it? This one says, what is the probability that the route we pick is exactly the 4 specific capitals? So probability is how many cases are there over the total. What these permutations and combinations do is they actually give you your total. Now if they just ask you how many ways, then you just put that answer in. But if it's probability and you have like 1 case out of this total, that's literally the answer here. Is 1 over this total. And the reason I know to do it is because it's asking for probability. 1 over this 35 million or whatever it was. 575. It was 3,575,880. And just do 1 over it because that's the probability. There's only 1 path that the candidate's going to take. So the probability they pick 1 path in particular is 1 out of this many choices. Is this practical? Certainly not, because 3.5 million is way too many. So it's the same deal. It's not practical because it's too large to do all that. It might be actually too hard to figure out what the shortest path is to take. A classic problem in statistics is how many different arrangements can you change up in a word? And let's take this word, for example, Mississippi. What this is kind of like is this is a combination of permutations and combinations, because some of the letters are different and some of them are the same. So it's not a full permutation or a full combination, because in those you all have either all different or all the same. So what we do here is you count how many letters there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. However many total letters you do that factorial in the numerator. Then in the denominator you do a factorial for every repeat. There are 4 letter I's, so I do a 4 factorial. There's 4 letter S's. And there's 2 P's. And there's 1 M, but it turns out 1 factorial is 1, so you don't even need to put the 1 factorial. A factorial, like 4 factorial, means 4 times 3 times 2 times 1. So I could do 11 factorial and have 11 times 10 times 9 times 8 all the way down to 1, 4 all the way down to 1, 4 all the way down to 1, and 2 times 1, and try to do all that out. Luckily, the calculator can do this for you also. The only thing is, when you tell it 11 factorial, type the 11, hit math, go to probability, and factorial is the 4th choice, right below permutation and combination. Divided by. Now, I'm going to do a bunch of things in the denominator, so you have to put parentheses around the entire denominator. 4 factorial. And then another 4 factorial. And then a 2 factorial. If you don't put the parentheses, it will only divide the first one. It won't divide all 3 of them. So the number of different ways you can rearrange Mississippi, there's 34,000 different ways. Again, this is not the probability of it. This is how many ways can you do it. 34,650. So I want to do that example first because necessary doesn't have as many repeated letters 1, 2, 3, 4, 5, 6, 7, 8, 9. You do 9 factorial. There's only one n, so forget that. There's 2 e's. There's 1 c, we can forget that. 2 s's. 1 a, 1 r, and 1 y. So this one's kind of a simpler example. All the 1 factorials don't matter, so you can just skip them. 1 factorial is 1, so multiplying by 1 or divided by 1 is not going to matter. So this one's a little simpler. 9 factorial divided by 2 different 2 factorials. Whoops, hit the wrong one. Back up and delete that. Math, probability, 1, 2, 3. Permutation, 2, math, probability. You can also just hit the 4 button to get it to say 4. So this answer is 90,720. There's 90,720 different ways you can rearrange letters in that word to create some kind of new message. Many of them wouldn't be real words, but it would be a different meaning at least. Okay, discrete and continuous, the way you tell these is discrete are things that you count. Continuous is measured. And everything else is neither. But sometimes it's hard to tell, do you count or measure it? There's another way I do these sometimes. Is the distance a baseball travels in the air after being hit a discrete, a continuous, or not a random variable? You have to be discrete or continuous to be a random variable. And distance is something we measure. Distance is measured. A ball might fly 300 feet, it might fly 301 feet. Another way I do these is think of 2 examples. A baseball could go 300 feet or it could go 301. Think of 2 examples right next to each other. Could you get in between if you wanted to? Yes, a baseball could go 300.8 feet. It's possible to be anything in between. There's an infinite number of values in between, so that's another reason it's continuous. Either because it's measured, or because I can get anything in between 2 examples. The amount of snowfall. Snowfall is a measurement. You could get 1 foot of snow, 1.1 feet, 1.01, it can be anything in between. That's continuous, and it's a measurement. Did you smoke in the last week? People are going to say yes or no, so you have to have numerical answers to do a random variable. So this is not a random variable because you don't count or measure yeses and no answers. It has to be a numerical answer. Is the number of points scored in a basketball game discrete or continuous? So somebody could score 28 points, they could score 29. I think of 2 examples close to each other. This one I could get in between. You cannot get 28.2 points in a game. It's impossible to get anything in between 28 or 29. So that's discrete, but you can't get in between them. Plus you count the number of points, you don't measure it. The number of light bulbs, same deal, that are out. There could be 3 light bulbs out, there could be 4, but you can't have 3.5 light bulbs out. This is discrete because you can't get in between 2 examples. Time required. Time, you might think, are you counting time? Are you measuring time? It seems like you're counting it when the seconds go by. 1, 2, 3. But time is actually measured. And we have stopwatches. We could go 6.8 seconds, 6.9. We could have 6.85, 6.853. If you can get more and more accurate if you wanted to, that's definitely continuous. Time is measured, and I can get more accurate in between examples. Unlike the points, you can't get more accurate on number of points scored in basketball. Okay, so that's the end of chapter 4. Chapter 5, we move to working with random variables. This is a probability distribution. The main idea on it is we want to find the average and the standard deviation of this probability table. You could use your calculator to help you here. If you go to Stat, press Enter for Edit. In List 1, type all the X values. 0, 1, 2, 3, 4, and 5. In list 2, put your probabilities. 0.0459, now here you got to be careful about typos. 0.1956, 0.3332, 0.2838, 0.1209, and 0.0206. Okay, first of all, to be a probability distribution, the first column has to be numerical, and it needs to be discrete where you can count it. I can get 1, I can get 2, but I cannot get 1.3 children to have a genetic effect. So the first thing to check is the first list discrete? And here it is. The second list are probabilities, so that's like question 1 on the review. None of these probabilities can be negative, and none of them can be bigger than 1. If any of them were, we would eliminate this and we would just click B. The table is not a probability distribution, if any of those were impossible probabilities. The third key to have a probability distribution is the sum of all probabilities needs to be 1. So you can either manually add all these decimals up and see if they equal 1, or a quick way to check it in here is hit second quit, second stat, go over to math. We did this in the last chapter with the mean and the median and the standard deviations. But I could do the sum of list 2 and see if that equals 1 or not. And it does equal 1. The sum of list 2 is 1. So this is a true probability distribution, therefore it will have a mean and a standard deviation. Here's how you find the mean the long way. Go back into stat and edit. I'm going to go over to list 3 and go up to the top. To find the mean, you need to multiply every x by every probability and add them all up. That's what the mean is. So to do it quickly, you can hit second L1 times second L2, and it'll do all 6 products for you at the same time. If you press enter, it just multiplied all 6 of them. 0 times this is 0. 1 times 0.19 is 0.19. The sum of all these list 3 numbers is the mean. So I can do it the same way I added up L2. Second quit, just to get out of the screen. Second stat, go over to math and choose the sum of L3. The mean is 2.3. That's supposed to represent the center of the table. The center of the table is actually about 2.5, but there's more probability in the bottom half. These 3 probabilities in the bottom half are slightly above 0.5, where these 3 are below 0.5. So instead of getting exactly in the middle for the average, it's a little bit to the lower side, 2.3. That kind of makes sense that the answer is 2.3. 2.3. Now the standard deviation takes a while to do the long way, so I'm going to show you the shortcut that can help you get both of these answers at the same time. After you put the numbers in list 1 and list 2, you don't even have to do list 3 if you would have done this. Stat, calculate, and choose 1 bar stats. And then, I don't know if this calculator is slightly different. It'll let me do this? No. Okay, so first hit calculate. And then what we need is, we need to give it this command again. So I'm going to hit second enter. So it comes up with this 1 bar stats. The problem is 1 bar stats does 1 list normally. It just does the list 1. But I wanted to do both list 1 and list 2 at the same time. So if I tell it comma, right here above 7 there's a comma. And then if you tell it list 2, 1 bar stats of L1 comma L2 at the same time. Notice that when it spits out all these answers, the sum of x, that is your mean. 2.3, there, that's the same answer I got before. So you can avoid doing the L3 if you just want to do this 1 bar stats of L1 and L2. And then the advantage is not only when you get the 2.3, you've got the sigma here too. Round to 1 decimal place. Make sure you read that so you don't miss that one. Round to 1 decimal place. 1.1 would be the standard deviation. Okay, on number 17, they got a table here again. And the first thing I notice is the x's seem to be discrete. 1, 2, 3, 4, 5. We're not getting anything in between. The probabilities all seem okay. They're all between 0 and 1. None of them are negative. None of them are bigger than 1. But what do the probabilities add up to? 0.001 plus 0.012 plus 0.133 plus 0.294 plus 0.449. It doesn't add up to 1, it only adds up to 889. That's not good enough. It has to add up to 1, otherwise it's not truly a probability distribution. So this one's kind of nice. I can just click B and say it's not even a probability distribution. It won't have a mean or a standard deviation if it's not a probability distribution. So you better check that first, otherwise you might be doing all that work for nothing. What kind of variable is a variable that has a single numerical value determined by chance for each outcome of a procedure? This is the definition of a random variable. It's determined by chance. We don't know what's going to happen. The random variable is the first list in the probability distribution. What kind of random variable has infinitely many values associated with it? This is continuous. Continuous is when there's an infinite number of possibilities in between two examples. So that's why you could never write them all down. Okay, so the next thing in chapter 5 is we have binomial distribution. And you can find probabilities for them if you recognize the input of a binomial. N is the number of trials. P is probability of success. And X is the number of successes you're hoping to get. And that's usually the three things they give you in the problem. So it says this one has a binomial distribution with 5 trials. The number of trials is 5. And the probability of success is 0.30. That needs to be a decimal or a fraction between 0 and 1 like all probabilities. It can't be negative, it can't be bigger than 1. Find the probability that you get exactly 0 successes. So your number of successes is 0. If you're trying to do exactly 0, there's a function in your calculator that will calculate exactly. It's called binom PDF. PDF is for exactly problems. And it simply needs N, P, and X placed inside of there. Some calculators will be a little more user-friendly and will have you type in each one. Sometimes you have to literally type it all yourself with commas in between. This calculator is the more user-friendly one. This is located under second vars, and you up arrow to get there quicker. It's the 5th one from the bottom, binom PDF, not CDF, but PDF. In this calculator, it says how many trials did I have? There was 5. Probability was 0.3, and then I'm hoping for X to be 0. When you hit paste, it takes you back to the screen and it has it typed for you. Some calculators, when you hit binom PDF, it takes you right to where the parenthesis is. And you might have to type a 5, comma, 0.3, comma, 0. You might have to type that yourself, or it might be like this where it does it for you. The answer, and it says round to 3 decimal places, 168. 0.168. So if you're trying to do an exactly binomial, you use PDF. Same thing here. What's the probability of exactly 4 when the brand name has a 40% recognition rate? And we're going to check this with 5 randomly selected customers. So our trials is 5. the probability is 40%, but notice it's percent. You can't put in a number bigger than 1 for probability, so you got to change 40% to a decimal. 40% is 0.40. And that's the P that you need. You can't put 40 and it's got to be a decimal. If it's bigger than 1, it'll say error. So I've got 5 trials, second vars, up arrow to binom PDF. 5 trials again, same, but now it's 0.4 probability, not 40, but 0.4. And we want exactly 4 successes. This answer to 3 decimal places is 077, because the 6/8 is going to round up to a 7. 077. 0.077. Find the probability that all of them are selected. So now we have 5 trials. 5 trials, 0.4 for a probability. We want all 5 of them to be a success. So you just change the x value to the next one. 0, 1, 0 to 3 decimal places. 0.010. Now, here's this last case. What's the probability that you get at least 4? At least 4 means 4 or higher. And all we have is 5 trials. So 4 or more means 4 or 5. Well, we just did both of those in the previous parts. Part A was the chance of 4. That was 0.77. Part B was the chance of getting all 5. That was 0.10. So you can just add these together and get 0.87. So that's the point of part B, is sometimes we don't do exactly one number. We might do some combined together. And then you can combine answers together from previous parts. Now, this last question here is getting you ready for a future chapter. If 5 consumers are randomly selected, is 4 an unusually high number or not? It is if 4 or more has a small probabilities. Anything less than 5% is considered unusual. We did not get less than 5%. Ours is 0.87, that's about 8.5%. If this is less than 5%, then you can say getting 4 is unusually high. But since it's not less than 5%, we can't say that it's unusually high. So no, because the probability of 4 or more is greater than 0.05. This is D. And it's not so important to know that in this chapter, other than getting this question right on the test, but you're actually going to see more of this when you get up to chapter 7 and beyond. That's why they're preluding it right there. Okay, there's a formula for the mean of a binomial. If you know you have a binomial and you want the mean, which the symbol for that is mu, it turns out it's just n times p. It's a lot easier than doing those means for the probability distributions, where you have to do them all in the calculator. And they tell you both n and p in this problem. N is 1504. P is 3/4, or you can change that to a decimal. Just literally multiplying these together gives you the mean. 3/4 as a decimal is 0.75. So I can do 1504 times 0.75. And the mean would be 1128 exactly. Now the formula for standard deviation, and these are on the formula sheet, so you don't have to memorize them. The standard deviation formula is square root of NPQ. If P is 3/4, this is the probability of success. Q is the complement. Q is the probability of failure. And complements are always 1 minus whatever you had. So the complement of 75% is 25%. So this would be the 15 number, 1504 for for n, p is 0.75, and then q is 0.25. You do all of that inside of a square root. Square root of 1504 times 0.75, that part's what we had before, but then also times 0.25. Round to one decimal place, 16.79, that's going to be 16.8. Now, here's another thing that's preluding to a future chapter. That idea about getting less than 5% in a probability is unusual. Another way to see that numerically is to take your mean, 1128. The answer we got for the mean was 1128. The standard deviation was 16.8. If you subtract 16.8 twice, this will get you down to the cutoff value that's considered unusual. It would be unusual in this problem to get a value less than 1094.4. So 1094.4 is literally the mean minus the standard deviation twice. And then the mean plus the standard deviation twice is the unusual cutoff on the upper side. So if you take your mean 1128, add the 16.8 twice. Anything beyond this is considered unusual on the upper side. 1161.6. So this problem was about, I guess it doesn't give me what it's about, but say this was like test scores on the SAT or something. If you get a score between 1094 and 1161, that's the usual range of scores. Anybody who goes above 1161 is considered unusual, and in that test, that would be a good thing. If you got less than 1094, then you'd be unusual, lowly unusual, which would be a bad thing on a test. But that's the point of this, is we get a range of values compared to our mean that we can tell right away is it usual or unusual. It's similar to the probability problems where if you're less than 5%, that's unusual. If you're more than 5%, it's usual. So that's the point of that problem, at the end of that problem. Okay, here's another one. A candy company claims that 25% of its plain candies are orange. There's a sample of 100. So they're giving me the N and the P, although the P is a percent. So this is the same problem as 23. The mean is N times P. Just make sure you change your P to a decimal. 25% is 0.25. N times P would be 25. And then if P is 0.25, then 1 minus 0.25 will be Q, the probability of failure. If 25% of these candies are orange, then 75% are not orange. And you need that for the standard deviation because it's square root of N times P times Q. 100 times 0.25 times 0.75 all inside of a square root. Round to one decimal place, 4.3. And that one didn't ask for, let's see if it does. Oh no, it doesn't ask for the mean minus 2 sigma at all. A random sample of 100 candies contains 18 orange ones. Is this unusual? Okay, so maybe we do need to figure that out. So if we take our, it's not asking for it directly, but we're going to figure this out. Take your mean 25, subtract 4.3 twice. Anything less than 16.4 would be unusual. Is 18 less than that? No. So 18 is not unusual. No, 18 is within the range of usual values. Thus, the claimed rate of 25% is not necessarily wrong. If it was unusual, then we could say that that claimed rate is probably wrong. That's the point of, also the point of getting that range. Okay, last thing on the test is something similar to binomial. There's another distribution called the Poisson, named after a French guy. And you can do a Poisson PDF just like a binomial PDF. but it only needs two entries. It needs lambda, which is the average, and x is the successes. So there'll be an average amount quoted in the problem, and then there's so many successes you're trying to get. And that's how the last two problems go. So assume that the Poisson distribution applies and that the mean number of aircraft accidents is 7 per month. So the mean or the average is 7. The mean number of accidents is 7 per month. Find the probability of 0. We want to try to make it through a whole month with no accidents. What's the probability we can get 0 accidents in a month? This is similar to the binom PDF. You hit second vars, up arrow until you get to Poisson PDF. And then lambda is 7 and x is 0, or maybe you have to type them in yourself. After you type Poisson PDF, if a parenthesis pops up, type 7 comma 0 if you have the older version of the calculator. Round to 6 decimal places because they got this E-4 again. The calculator is saying 9.1188 E-4. Don't forget to look all the way at the end. 9.1188 E-4. That means you got to move 4 to the left. 1, 2, 3, 4. It'll give you 3 zeros first. 1, 2, 3, 4, 5, 6. There is an 8 after that, so we got to bump that last one up to a 2. 0, 0, 0. 912. And is that less than 5%? Yes, this is way less than 5%. So is it likely to have a month with no accidents? No, it's unlikely because this is a very low probability. It's very unlikely that this would happen. We're probably going to have at least one accident, unfortunately. So that's what these things can tell you. Exact same thing in number 25, except the number of accidents per month is 10. So now we do this with 10 as the average. And then instead of no accidents, they want the probability of 6. So it doesn't have to be no accidents, it could be any number between 0 and 10. So Poisson PDF, second vars, up arrow to it. Always pick the PDFs. 10 and 6. This one wants it rounded to 4 decimal places. 0, 6, 3, 0, but there's a 5 next. So 0, 6, 3, 1. Be careful, that's the first problem in the whole review where they asked for 4 decimal places. Every other one's been 1, 3, or 6. Always read that before you submit an answer. And 0.6, so is this less than 5%? No, it's not. So to be unlikely, it has to be less than 5%. So if it's not unlikely, we could consider it likely, but really 6% isn't all that likely, but we can definitely say it's not unlikely. You have to be less than 5% to be unlikely, otherwise you say it's not unlikely. So in other words, it could happen. We could see 6 accidents in a month for this problem. Okay, so there's all 25 questions. All 25 are correct. Practice this a few times before you take the test. Send me any questions you have. Definitely read carefully what they want for an answer every time. Also, it takes some practice with the calculator to know these shortcuts because you kind of have to memorize them when you're in the middle of a test. Sometimes we hit second stat, sometimes we hit second var, sometimes we hit math. So watch the video a few times, pause it when you get the problems, and then you should be able to do well in this test if you know all the calculator shortcuts. I'll be doing another review when the third test gets closer. Stay tuned for more action.